Hello again. It's been a while. I'm sorry. I haven't been able to record a new lecture for the past few weeks. Things are starting to, at least we have a hope that things will go back to normal, but please don't hurry about it. Take care of yourself. Don't think that it is safe. Just be careful. Don't hurry about getting back to your normal life. Okay. Now we are going to, in this video, we are going to talk about a new method of solving differential equations. And probably, if you're an engineering student, this is going to come up in your other courses. So we are going to talk about Laplace transform. It is a special transform. In general, we call them integral transforms. So in order to talk about this transform, first we need to recall some facts about improper integrals from calculus. So if you remember from calculus, when we talk about improper integrals, to have a proper integral, we need a bounded, closed bounded interval and a bounded function on that interval. So if one of those conditions are violated, then we have an improper integral. For Laplace transform, we need to talk about improper integrals when the interval is infinite. So basically, we are going to talk about the improper integral from some real number a to infinity of a function, one variable function, real valued. So we define this to be the limit as m goes to infinity of the integral from a to m of the function. So what we do really is, so we have some function. It doesn't have to be positive. So some number a to infinity, instead of taking the interval to infinity, we take the integral up to a number m, then we take the integral of the function, and then we let this number m go to infinity. So of course, for some functions and for some functions, this limit exists, and for some other functions it doesn't exist. So if the limit exists, we say that the integral is convergent. The integral is convergent. Or the integral converges. To this limit. Otherwise, if the limit doesn't exist, we say that the integral diverges. Okay. We will, when we define Laplace transform, we will have a chance to consider examples of improper integrals. So I'm not going to do examples now. All right, but to talk about improper integrals, we need functions which are integrable on finite intervals, so that we can take the integral from this number a to the number m. And basically, these are going to be piecewise continuous functions. So what is a piecewise continuous function? Okay, so let f of t be a function defined on the finite interval AB. So first, we talk about piecewise continuous functions on finite intervals. We say that f is piecewise continuous on AB if we can divide the interval into finitely many subintervals. So if there are finitely many points, say A0, A1, up to AN, such that first of all, the numbers must divide our intervals. So the first number should be the initial point of our interval A. Then they are going in an increasing order. And the last one should be the endpoint B. So these numbers divide our interval into n subintervals so that our function f is continuous. Continuous on each interval. But for the interval, we take the open interval. When I give you the examples, it will be clear. So on each open interval, our function is continuous. So that means at the endpoints, at these number a's, we may have discontinuities, but discontinuities should be in the form of finite jumps. So the reason shouldn't be that the function becomes unbounded at those points. So our third condition to call the function piecewise continuous is that at each of these points, the limits as t approaches the endpoint from left or from right should be finite. So these limits exist for I between 0 and n. And for I equals 0, A0, remember, is the endpoint A. So at the endpoint A, we can only look at the right limit. And when I equals n, that endpoint is B. And at the point B, we can only look at the left limit. So we expect these to exist also. Exist means finite. So there is a number. So basically, a piecewise continuous function. So we have an interval AB. So we take A is A0, and then A1, A2, some points, and the last one is AN. So at the point A, we have a limit, but the function doesn't have to be continuous at the point A. So the graph may be something like this, but from A to A1, it has to be continuous. It has to be continuous, and it must have, at the point A1, it must have a left limit and also a right limit. But the left limit doesn't have to be equal to the right limit because the function doesn't have to be continuous at A1. But in the open interval from A1 to A2, it has to be continuous, and then so on. So the previous one, again, it may be something like this. Okay, so it shouldn't be, so this graph is piecewise continuous. But at the points, it shouldn't be like, say, we divide the interval only 2 pieces. So it shouldn't be like this. Oops. I'm sorry. Oops. Yeah. So something like this wouldn't be piecewise continuous because at the point A1, at the middle point, okay, it is not continuous, but it doesn't have a left limit at the point A1. So this is not piecewise continuous. So we don't want our function to become unbounded. It has to stay bounded. So at the points A0, A1, A2, it may only have jump discontinuities. So piecewise continuous functions may only have jump discontinuities at A0, A1 up to AN. Okay. Now, examples of piecewise continuous functions. So concrete examples. So examples. Say the interval from 0 to 2, and at the midpoint 1, let's take a simple function like this. And we may have a jump discontinuity at at 1. Okay, so something like this is piecewise continuous. On the interval 0, 2. Something which is not piecewise continuous, as I already indicated on the graphs on the left. So on 0, 1, if you have something like this, it wouldn't be piecewise continuous. So this is not piecewise continuous. On 0, 2. Okay, another reason for a function being not piecewise continuous, it may have jump discontinuities, but you see the points on the finite interval, the points of jump discontinuities should also be finite. If you have infinitely many, for example, consider the function. It is 1 if t is in the interval 1/2n, and 1 over 2n minus 1, and 0 if t is in the interval 1 over 2n plus 1 and 1 over 2n. So here n goes from 1 to infinity. Okay, so this function is not piecewise continuous. On the interval 0, 1, it has jump discontinuities. At infinitely many points. You see at each of these points, 1 over 2n or 1 over 2n minus 1, it has a discontinuity. So the function goes like, okay, let's see. So for n equals, we are considering the interval 0 to 1, then we have 1/2, 1/3, 1/4, 1/5, and so on. So in the interval where t is, okay, let's see. For n equals 1, between 1/2 and 1, oh, I see. And we need to define f of 1. So let's say f of 1 is 1 and f of 0 is 0. We need to define those two. So in the interval 1/2 and closed at 1/2 to 1, it is open when you look at here, but f of 1, we define it to be 1. So it is 1 here. So from 1/3, from 1/3 to 1, at 1/3 it is 0. And from 1/3 to 1/2, open at 1/2, the function is 0. Oops, maybe I should choose a different color. Yeah. And in the interval from 1 over 4 to 1/3, again, it is 1, closed at 1/4, open at 1/3. From 1/5 to 1/4, it is 0 again, and so on. So the intervals are becoming smaller. But you see, at infinitely many points, at 1/2, 1/3, 1/4, 1/5, and so on, the function f has jump discontinuity. So something like this is, again, not piecewise continuous, because on the finite interval 0, 1, it has infinitely many jump discontinuities. Okay, how about if we take an infinite interval instead of taking a finite interval like 0, 1, 0, 2? How do we define piecewise continuous functions on infinite intervals? A function f of t is piecewise continuous on an infinite interval if it is piecewise continuous on every finite subinterval. So on this infinite interval, the function may have jump discontinuities at infinitely many points, but on any finite subinterval, there must be only finitely many of those points. An example similar to the one above. So 1, if t is between an even integer and an odd integer for closed at the even integer and open at the odd integer, and 0 if it is the other way around. And here n is any integer. So for n equals 0, between 0 and 1, it is 1. Okay. Between 0 and 1, it is 1, closed at 0, open at 1. And between 1 and 2, it is 0, closed at 1, open at 2. And between 2 and 3, it is 1 again, closed at 2, open at 3. From 3 to 4, it is 0, closed at 3, and so on. So it keeps going in the other end like this. And so on. You see, f is discontinuous at every integer, but on any finite interval, there are only finitely many integers. So on every finite interval, f is piecewise continuous. So this function is piecewise continuous. On all of the real numbers. Okay. Now, the reason we consider piecewise continuous functions is because piecewise continuous functions are integrable. I'm not going to prove that. This is, well, even for calculus, it may be too much to prove this. It's a topic for advanced calculus course. If f is piecewise continuous, on a finite interval AB, then f is integrable on this interval. That means the integral from a to b of the function f exists. From calculus, you know how to evaluate this integral. We just evaluate it on every subinterval where f is continuous and add them up. And now, to decide whether whether an improper integral is convergent or not, sometimes we cannot evaluate that limit in the definition because we cannot figure out the integral of the function exactly. So sometimes we may have to decide about convergence or divergence without evaluating that limit. And again, if you remember from calculus, we can do it by a comparison. So let f of t and g of t be piecewise continuous on the infinite interval a to infinity. such that when you look at the absolute value, the function, we are going to say something about the improper integral of the function f. The function may not be positive on that interval, but in order to use this theorem, the function g must be the function we are comparing f with. So let's say the absolute value of the function f is always less than or equal to this function g for all t in this interval a to infinity. And suppose the integral from a to infinity of the function g converges. So we have a function g which dominates the absolute value of the function f, and the improper integral of this dominating function is convergent. Then the result is the improper integral of the function f is improper integral of f also converges. So the absolute value must be less than this function, and this function is convergent. That implies the improper integral of f is also convergent. And now we are ready to define the Laplace transform. First, maybe let me say a few words about why we are doing such a thing. So what we are trying to do, we have a function f of t, so usually we denote it by the variable y, and we have a differential equation, satisfies a differential equation. So we are trying to find a general form of such a function, which all functions which satisfies this differential equation. So this everything here goes on in t space. So our variable, independent variable, is t or x or whatever. So the idea is apply a transform, apply some procedure, some operation. It's a function, in fact. Apply a function to everything. So change everything to another space. It is going to be the variable we are going to denote by s. So we also change the differential equation by this transformation, and the differential equation becomes a linear, algebraic equation. No derivatives, it becomes an algebraic equation. Algebraic equations we can solve. So solve this equation and go back. So we cannot solve the differential equation. We apply a transformation. We change the equation. And hopefully, if we choose the correct transformation, this equation becomes an algebraic equation. And we solve that equation. And we go back to the t space to interpret our solution as the solution y of the differential equation. So this is the main idea. Of course, you can do it in various different ways, and one way is to use integral transformations. So first, an integral transform changes a function f of t into a function I'm going to denote it by capital F of S. So we are changing the independent variable also. We have a different variable S. Since it's an integral transform, we do it by means of an integral using a function. So we use a function K of two variables, S and T. So basically what we do, we take a function of two variables, integrated on some interval with respect to T. So the resulting function becomes a function of S only. So into a function capital F of S using a function K by the integral. So F of S is you choose yourself a certain interval from alpha to beta, and then you multiply this function of two variables with your function F of T, and integrate the result with respect to T from alpha to beta. Since you have a certain interval, the resulting expression doesn't depend on the variable T. It's going to be a function of S only. So this is in general an integral transform. Now, a Laplace transform is a special integral transform. So first, we need to consider piecewise continuous functions. So let f of t be a piecewise continuous function. And as the interval, we take the interval from 0 to infinity, so positive or non-negative real numbers. Then the Laplace transform, so we use this funny L of the function f of t, which we are going to denote by capital F of S, is the integral from 0 to infinity. You see, for the integral transform, I need a function of two variables. And for Laplace transform, I use the function e to the power minus st multiplied by f and integrate. So this integral, this function is called the Laplace transform of the function f of t. So given a function f of t piecewise continuous on the infinite interval from 0 to infinity, we multiply it with the function e to the power minus st. Then we look at the improper integral. Of course, this improper integral may converge or it may diverge, and that also depends on the value of s. So Laplace transform of f of t is defined for those values of s for which the improper integral converges. Result is a function of s, and as the domain of that function, we take the values of s for which the integral is convergent. So let's start with examples to understand more clearly what is going on. So as the first example, we look at the easiest case, Laplace transform of the constant function 1. So we take the constant function. It is 1. My 1 is funny. Okay, 1. Okay. All right. We use the definition. So Laplace transform of the constant function 1. By definition, it is the improper integral from 0 to infinity of e to the power minus st times my function, which is 1 times dt. How do we evaluate this improper integral? We write it as a limit as m goes to infinity of the integral from 0 to m, e to the minus st dt. Well, this function is easy to integrate, and antiderivative. I'm integrating with respect to t. So the exponent of the exponential function have minus s in front of t. So I need to divide by minus s e to the minus st for t from 0 to m. So if I substitute m for t, e to the minus sm minus, if I substitute t equals 0, e to the power 0, which is 1. So I need to take the limit as m goes to infinity of e to the power minus s times m. Here we regard s as constant. Now, so think about this limit. So limit as x goes to infinity of e to the ax. X is multiplied by a constant. If that constant is positive, the limit is going to be infinity if the constant is positive. And if it is negative, it is going to be 0. Because then 1 over exponential function, and it goes to infinity, so 1 over the exponential function goes to 0. So if this coefficient of x in the power of e is negative, then the limit is 0. And if this coefficient is 0, you have the constant function 1. So the limit is 1 if that constant is 0. So basically, we are going to consider the case when this number a is negative. Now, in our limit, the coefficient is minus s. So this is like the number a in this limit. So this limit is going to be, the limit of the exponential piece is going to be 0. So the limit is going to be 1 over s if minus s is negative. That means s is positive. So we, and otherwise, okay, if s is 0, that's true, this limit is going to be 1, but if you go back to the improper integral, if s is 0, then the improper integral is going to be from 0 to infinity, e to the minus st dt. When s is 0, e to the 0 is 1, so this becomes improper integral of 1, which is infinity, divergent. So I cannot consider the case s equals 0. So this means the Laplace transform of the constant function 1 is the function 1 over s, and it is defined only for s greater than 0. So this is our first formula, if you want, of Laplace transforms. And in the remaining of this lecture, basically, I'm going to get Laplace transforms of some other elementary functions and give you a condition for when we expect this transform to exist. So this is going to be the content of the second part of the lecture, and that's all for part 1.